Hello and welcome back after some time. The next chapter on Young measures will be devoted on analysis on metric spaces. But the first video I wanted to devote to just the definition and framework of what it includes. To begin with, analysis is a broad subject nowadays in mathematics, and basically it covers everything that is not algebra, that is not group theory, ring theory. Any kind of math that has to deal with continuous functions, limits, sequences, measures, series is a subset of analysis. But when it comes to analysis on metric spaces, what do we exactly mean? And that was a question asked on Overflow, and fortunately one of the leading names in the theory has provided a direct answer to this. So I want to just emphasize the main parts of this. So non-smooth functions, Piotr Hajwasz writes, have been studied in analysis since the 19th century. But then that talks about Sobolev functions, which are functions that are not smooth in the traditional sense, but still they have a notion of derivative which is good enough and which turned out to be very, very important to PDEs. Actually, PDEs are just nowadays synonymous with Sobolev functions. But then there is something here happening, and it says that the non-smoothness here comes from functions and not just the spaces where they are defined. They are still defined on Euclidean objects. So the first attempts to talk about some form of analysis on metric spaces that are not necessarily Euclidean or manifold was happening, I think, around 70s. But then again, this is not completely full strength analysis because it only deals with zero order analysis in the sense that it doesn't talk about derivatives. So if we think of analysis as an upgrade of calculus, then we're having integrals here, but no derivatives. Therefore, beginning in 90s, people started talking about Sobolev functions on spaces that are also not smooth. So putting differentiable, in some sense, functions on general metric measure spaces. And given that it started in the 90s, it's a rather recent field, but it was recognized in 2010 as a subcategory of itself, and given this MSc classification, Math SciNet classification 30L. I have talked about Math SciNet as a tool, but I hope many of you at least know what this means. Okay, a rather recent kind of summary or global viewpoint of analysis on metric spaces was written by Bang, Caponia, Hajwasz, Shanmuglingham, and Tyson. So they were among the founders of many of the theories. And here is that maybe 4-page or so note that they had written. This was part of a conference, or rather a long-term workshop called Analysis in Metric Spaces. And I was lucky to be part of that workshop. And this document is available on arXiv as well. So the motivation started in 90s from the study of quasi-conformal mappings, and Heinonen and Koskela were interested in generalizing certain facts about quasi-conformal mappings from Euclidean setting to more general metric settings, and they came up with notion of upper gradient, and as they write here, the groundbreaking work from 1998 initiated the modern theory of analysis on metric spaces. In this short note, they cover certain aspects of analysis on metric spaces in different subsections. Maybe the first or the most significant object to look at on a metric measure space is whether that metric measure space supports Poincare inequalities. And the Poincare inequality is a space supports a Poincare inequality if the average oscillation of a function from its average values. So you take a ball, u subscript b is just one number, which is the average value of the function. So you take this difference of function from the average value, you take absolute value, and you integrate again, you take average. These are just technicalities. And the core idea is that the oscillations of the functions are controlled by integral of the derivative of the function, but this is in a very general sense. So this is, we'll talk in detail, of course, all about these objects. But yes, so in order to have a fruitful theory of Sobolev functions on a metric measure space, you like your space to support some sort of inequality of this sort with some exponent p and a universal constant capital C. So Poincare inequalities, what spaces support this, what supporting a Poincare inequality implies about a space have been studied intensively, and there are great results in this direction. The next thing is, as was mentioned already, that some nonlinear potential theory can be done on metric measure spaces. We can talk about harmonic functions in a generalized sense. What they call here is P quasi-harmonic, and sort of calculus of variation type of questions can be framed and studied. Another very significant and extremely famous among the analysis circles paper is paper of Cheeger from 1999, where he proves that in spaces with some sort of nice geometry, Lipschitz functions from the metric space into R, say, can be differentiated. And this generalizes Rademacher's theorem that I have previously covered in my videos on area formula, for example. So that is another big achievement of the theory. There is bi-Lipschitz embedding theorems, which I want to pass up on. So geometric measure theory. This brings to mind area formula, coarea formula, rectifiable sets, density of measures, identifying rectifiable sets and rectifiable measures. But those questions can also be naturally asked and answered in metric spaces. It's even easier to talk about geometric measure theory in metric spaces. You don't need to even define completely new objects, because the main objects of studying geometric measure theory are Lipschitz functions, and Lipschitz functions are defined just as they were defined between Euclidean domains. The biggest maybe theorem that allowed many of the results to be generalized was what is called metric differentiability due to Kirchheim. He proves that if you have a Lipschitz function from Euclidean space into an arbitrary metric space, then you can take derivative in a suitable sense. And with that derivative, you have area formula, and also in 2008 and 9, it was proved that you even have the coarea formula. And the last subject that they single out is dynamics on metric spaces. So this talks about limit sets of rational maps, the Julia sets, attractors, and these you may have seen in Euclidean setting, but you can also study them on metric spaces. Some work of Bang here, Bang and Kleiner, is significant. They have some results regarding uniformization of spheres. So you have a space that topologically and maybe also from point of view of Hausdorff, two-dimensional Hausdorff measure, looks like a sphere. So it has the right necessary conditions to be homeomorphic to the sphere. And then you ask when you can have a quasi-symmetric map between your space and the honest two-dimensional sphere sitting in R3. So quasi-symmetric maps are generalization of bi-Lipschitz maps. So when you find a quasi-symmetric map between two objects, to some great deal of detail, they share many properties. And finding such theorems that under this condition and that condition, this space is quasi-symmetric to a familiar space like a Euclidean space or the Euclidean sphere are important, and they are often called uniformization theorems. So that's just, as they say, a brief note only of what kind of questions analysis in metric spaces covers. To conclude, if I want to add anything, is analysis on metric spaces is, say, different from PDEs in the motivation and in the type of questions that it tries to ask and answer. Analysis on metric spaces, by its very nature, is very closely related to geometry. As I said, the original motivation for even defining them came from quasi-conformal mappings, which are some geometrically defined maps, and you wanted to prove some nice properties for them, and going through analysis through their analytic properties was one effective way of doing so. And in any of the items that we saw in this note, for example, there's always that geometric aspect to it. My goal is to mainly focus on Poincare inequality and doubling measures, and give you as many examples, starting with very simple subsets of Euclidean spaces as possible, to illustrate the now well-known fact that Poincare inequalities are very, very essentially linked to the geometry of a space. Whether a space satisfies a Poincare inequality or whether it satisfies a Poincare inequality with some critical exponent P appearing here in this inequality is linked inherently to the geometry and measure on that space. And still there are questions, and there are papers coming out even every month related to such problems. So it's a beautiful area of research that you can familiarize yourself with. You can read on your own. You can also follow the sequence of videos that I hope I will be able to upload quite regularly in the coming weeks. So if you have any questions, please put them in the comment. If you have previously seen these objects or read about them somewhere, you could also comment why and how they appeared in your study. Hopefully this will be useful, and I can't wait to do the next video, beginning with core definitions and hopefully definition of the Poincare inequality. Thanks for watching.